So thank you everybody for joining us. This is our second of our newly introduced MECI Alliance seminar series. It's our way to, in this unique time, continue to have the intellectual stimulation that we all need and thrive to do our research, our business, and our education. Lenan Zhang is a doctoral student in mechanical engineering. He's working with Professor Evelyn Wang. He earned his master's degree in mechanical engineering from MIT. And today he's going to share with us his very interesting work in ultra-high efficiency desalination via a thermally localized multi-stage solar still. Please hold your questions to the very end. You can ask questions either by raising your hand via the chat function or using the chat function or raising your hand. And with that, I will turn it over to Lenan. And thank you very much. And we look forward to your talk.
Okay, hello everyone. Thanks, Sarah, and thanks, Brian, for your coordination, and thanks for the attending for everybody. It's nice to talking with you today. My name is Lenan Zhang. I'm working with Professor Evelyn N at West Research Lab in the Department of Mechanical Engineering. So yesterday is Earth Day, we all know. Today I would like to show you our group's gift, special gift for the Earth Day, and that is ultra-high efficiency desalination via thermally localized multi-stage solar steel. So let's firstly start from the water problem in the world. So we know that the global water scarcity is actually huge challenging to all around the world, since like more than 1/3 world population is actually heavily affected by the water shortage. This can be clearly seen from this picture that currently many countries worldwide are facing like different level of water shortage. So that is the reason that why the clean water supply and management has become one of 17 sustainable development goals launched by the United Nations in 2018. So we know that to address this challenging, like it's not only relies on the great involvement of everybody in our daily life, but more importantly, the scientific and technological level improvement breakthrough is always the driving force to make a difference. So for this reason, like there are many techniques developed to produce and supply clean water, and seawater desalination is one of the most effective approaches. Think about that there are actually more than 70% areas of Earth is covered by the ocean. So it is natural to think that extracting clean water from seawater it can be an effective approach to get a sustainable source. So in fact, there are already several commercially available large-scale seawater desalination technologies, which serves as a reliable water source for many countries already. So these technologies include the multi-stage flash, multiple effect distillation, and reverse osmosis. So in particular, the first two approach, the multi-stage flash and multiple effect distillation, using the thermal energy to drive the liquid vapor interface and also collect the condensed water to get the drinkable water. And for the reverse osmosis, as shown here, like we extract the clean water from the seawater just by applying the pressure to push the salt water through a semi-permeable membranes. Like although like all these kind of technologies works very well in many conditions, but we know that they need well-established infrastructure, such as the such as the electrical grid, and also the very sophisticated water transport and supply techniques. They need centralized installations to like combine many facilities together, and definitely, as Brian said, that they need like significant energy consumptions. So this means like the only very rich regions or well-developed countries can afford such requirement. That's why, like you can see from this picture, like this kind of large-scale technology are typically applied by the Middle East, like North America and Europe. However, think about the rural area, which is underdeveloped. So it is possible that they even don't have access to electricity. So it is fundamentally like challenging to implement this kind of like large-scale desalination technology to address the local water shortage. So that's why recently people focus more on the opportunity for the passive small-scale device to produce clean water. So very recently, the passive small-scale device for the solar vapor generation was enabled by the solar-driven interfacial evaporation. So this solar vapor-driven interfacial evaporation, particularly typically using a floating structure as evaporator, just as shown like this. This structure has 3 key features. Firstly, this structure is a porous structure, so it has many papillary channels. So as it can generate great papillary force to drive the bottom bulk liquid to the top interface. And in addition to that, this material has a very high solar absorptance, so it can effectively convert the incident solar flux into heat and drive the evaporation. Meanwhile, it has low absorptance in the infrared band, so the thermal radiation loss due to the elevated temperature can be minimized. And thirdly, this material typically has very low thermal conductivity, so the energy loss or conduction loss from the top interface to the bottom is minimized as well. But combining those 3 key features, so the thermal energy can be effectively converted and localized within this solar absorber, within this evaporator, and this enables to the interfacial evaporation with very high production rate. Combining this state-of-the-art evaporator with a condenser and put them into a closed system just like this, people have already developed several passive small-scale device which can produce clean water from the seawater. However, there are still several limitations, meaning there are 2 limitations for this kind of passive solar desalination technique. The first one is that the efficiency of the water production rate is still relatively low, especially compared with the well-developed commercial large-scale setup. And here we define the energy efficiency as this, it is just the total energy containing the produced vapor or water over the total input solar flux. And the reason for this low water production rate, meaning from 2 resources. The first one is when we pack this evaporator with a condenser into such a closed system, there are extra thermal transport resistance due to this closed system. Firstly, there is a transport resistance of vapor from the evaporator to the condenser. This was not shown in the just evaporate in the ambient condition. And secondly, so there is always inevitable loss during the water collection from the condenser. This is the first reason, and this can reduce the energy efficiency from 90% to even 50%. And the second reason sets the fundamental limit. So when the vapor condensed on the condenser like this, it releases the vaporization enthalpy. So in theory, it is possible to reuse this vaporization enthalpy to drive more evaporation and therefore boost energy efficiency. However, for most of the system, this vaporization enthalpy is lost to the environment. So this situation actually set a fundamental limit to the energy efficiency below 100%. So this is about the low water production rate. And the secondly is about the low flexibility for the choice of material. As we mentioned that for ideal design, the evaporator needs 3 features. It has selective spectral absorptance, it has good weightability to supply the capillary force, and it should have high thermal insulation properties. So it is not easy to combining all 3 features into one material simultaneously. So the commercially or existing available material is limited. That's why people work very hard previously to fabricate new material using material synthesis or fabrication. For example, people using the self-assembly nanoparticles to enhance the solar absorption as shown here. And people also fabricate the hierarchically nanostructured hydrogel, which enable the fast water transport and improve the thermal insulation. Although those materials are pretty good and working well and works very well, but they are in laboratory scale. They are not commercially available and they are not scalable. So this gives some practical challenging to produce very low cost and durable device. So for address those 2 limitations, our group think about the thermal aspect, thermal perspective. So that's why we propose this thermally localized multi-stage desalination technology, which just combines the interfacial vapor generation with the vaporization enthalpy recycling. Here we show the basic structure of our prototype. And it consists of 4 key components. This is a silica aerogel, the solid absorber, the capillary weight, and the condenser. Is a very, very simple structure. And basically, it has 2 key features. Firstly, instead of combining all the functionality into the evaporator, we decouple them. And we use the silica aerogel as a thermal insulator for the solar absorber, because the silica aerogel has very high transmittance for the solar irradiance, but it has a very low thermal conductivity. So it's a very good thermal insulator. And for the solar absorber, we just use a commercially available spectral selective absorber to convert the solar energy into heat and transfer the heat to the capillary weight. And we use a common capillary weight, which has good water transport property. And this weight the evaporation can occur on this very thin film, and all the thermal energy is localized on this weight. So by combining all those 3 functionality, we can get a very high evaporation performance in the single stage. And then after the vapor will transport through the air gap between the evaporator and the condenser, and then release the vaporization enthalpy after the condensation. So this to recycle or reuse this vaporization enthalpy to drive more evaporation, we just put this multi-stage structure into a ring, just showing like as this right-hand side. As you can see, like every time the released energy from the previous stage can be reused by the next stage to drive more evaporation. Due to this multi-stage design and this multi-stage desalination structure, we can get multiple time enhancement of total vapor and water production rate. So those are the basic design, but to have the better fundamental understanding about the performance and the corresponding optimization strategy, we developed this heat and mass transfer coupled model for the device level optimization. So we just simply considering the energy balance between the evaporation heat flux and the various heat loss, for example, conduction heat loss from the side wall, and the heat loss from the front wall in each stage. And in this way, we can solve the corresponding temperature rise, vapor flux, and heat loss in each single stage. And then we got the overall efficiency of the entire system. So there are several key parameters are of particular interest for optimization. Firstly, we want to know like how many numbers we need, the number of stages we need to get the desired performance. So it cannot be too much because we need to consider the material cost, but it cannot be too small because we want to improve the performance. So there are definitely an optimal principle for the number of stages. And we want to know the ideal air gap thickness to optimize the transport performance. And we also want to know how much thermal insulation is required to maintain a relatively high level performance. So that's why we run this simulation several times to get the optimization principle. And actually there are several interesting insights can be gained from the model. As shown in this figure A, like we show that the energy efficiency increased to a plateau with the number of stages. That means like the benefit of adding more stages is insignificant if your total number of stages is high enough. For example, like if you use like 30 stages in your design, like adding more stages has no like effect to improve the overall energy efficiency further. However, like even your number of stages is not that much. For example, you only use 10 stages, you already get good enough performance. This is like more than 70% compared with the plateau or the peak value of the energy efficiency. And secondly, like we varied the air gap thickness, and we see like the energy efficiency firstly increase with the air gap thickness and then drop down. So and then they're leading to a global optimal point represented the maximum like energy efficiency we can achieve. And this increased trend can be understood by like the reduction of the heat conduction loss with the increase of the air gap thickness. However, this decrease trend is resulted from the increase of the vapor transport resistance due to the air gap thickness. And as you can see here, for this configuration, the global optimal point corresponding to an air gap thickness about 2.5 millimeter. And thirdly, like we want to talk about the importance of the sidewall thermal insulation. As you can see, like even the moderate thickness of the sidewall thermal insulation can give you a significant enhancement of the total energy efficiency. And for example, if we can only use 1.3 centimeter thick thermal insulation with 0.02 watt per meter per Kelvin thermal conductivity, the energy efficiency will increase from about 300% to more than 400%. This is a quite incremental increase with just ending the thermal insulation. And based on these insights we gained from the model, so we set our design target. We plan to build a device with a height of 10 centimeters and air gap thickness 5 millimeters using 10 stages configurations. And we will put about 1.3 centimeters thick thermal insulation on the sidewall, and the desired predicted efficiency will be 470%. So please note that we use the air gap thickness 5 millimeter instead of the optimal 2.5 millimeter in practice, because we want to avoid the condensed droplets be reabsorbed by the evaporator. That's why we increased this air gap a little bit. And then I would like to show you our prototype. It's a very tightly packaged 10-stage prototype as shown in the figure A. And we use the nylon frame to support the selective spectral solar absorber at the front, and we put the optically transparent silica aerogel in front of the solar absorber, and then we put the anti-reflection coated glass at the very top to cover the overall device. And here we show that each stage it's just a modulus design because it's very easy to assemble or disassemble. And to enable the fast water collection and condensed water removal, we coated the hydrophobic coating, that is a Teflon, on this aluminum plate. And in this way, we can enable the dropwise condensation, as you can see here. Since the contact angle hysteresis is only 5 degrees, so the droplets condensed on the surface can be effectively removed by the gravity and collected at this bottom slots. And the accumulated water will flow out of this stage through this outlet as shown in this corner. And as I mentioned, we decoupled the functionality of solar absorption, thermal insulation, and the water transport. This enables us to choose very common material as a evaporator. And in this work, we just use a paper towel as an evaporator. It's very cheap and it can be reused by many times, but it has good water absorption and transport capability. And we show that there are many microstructures of the paper towels which can provide strong capillary pressure. And we also validate the optical property of the optical performance, as you can see in the figure E. The solar absorber has very high absorptions for the solar spectrum, but for the infrared band, the solar absorptions has very low emissivity. And for the silica aerogel, it has higher than 95% transmittance in the solar band, but the transmittance suddenly drops down almost to 0 for the infrared band. This can further reduce the thermal radiation loss using this silica aerogel. Combining all those very simple and commercially available materials, the total material cost of our unit device is only $1.5. This device is 10 centimeters times 10 centimeters area. So to be honest, this is not a so cheap price, especially considering that the unit price per area. But we should note that there are more than 70% of the total cost comes from the nylon frame, since we use a 3D printed nylon frame just for simple fabrications. So that means in the future, there are plenty of room to further reduce the total material cost by just replacing the nylon frame by other alternative and low-cost materials. So here we characterized the performance of our test in the laboratory well-controlled condition under the 1 sun illumination. The 1 sun here means that the solar flux is 1,000 watt per meter square. And we use a solar simulator to provide the solar flux, and we placed our device on a platform as shown like this. And there is a liquid reservoir beneath, and the evaporator of each stage contacts with the liquid. And to measure the energy efficiency and the water production rate, we use a balance to measure the mass loss of the reservoir. And meanwhile, we use many thermocouples to monitor the temperature evolution of each stage to get a better understanding for both the thermal and mass transport performance. And here we show the temperature characteristics during the experiment. As you can see, that the first stage, the temperature immediately rise up to the 60 degrees C and then maintain to their thermal steady state at 70 degrees C. And this is a very high temperature, can supply a very high vapor concentration and enable a very effective vapor production. And then the remaining stages are activated gradually, and they rise. The temperature rise can be seen here, and they gradually reach their thermostatic state as shown here. And after about 1 hour, all 10 stages are thermally excited and reach their thermostatic state. And meanwhile, we measure the mass loss of our stats, of our device using the balance. And we will further convert this mass change to the water production rate and energy efficiency in the future. And based on this mass and thermal characterization shown here, like we can get the temperature profile across in different stages. This is almost a linear temperature decay as shown here. And we can also measure the vapor flux generated at each stage. And as you can see here, the first 3 stages contribute to the more than 45% of the total water production. This further validates our comments about ending more stages is not always beneficial to further improve the performance, since you can see the rest of the last several stages has relatively low production rate. And then we converted the mass change to the energy efficiency using the equation I introduced previously. And as you can see, we demonstrate a record high energy efficiency at 385%, corresponding to the steady state production rate at 5.78 liter per meter square per hour. So to have the direct feeling of how much improvement we made, we compared this efficiency with the one-stage device performance. So as you can see, the one-stage device performance has about only 80% energy efficiency. This means it's about 5 times improvement we achieved using these multi-stage structures. And we also want to emphasize the importance of the sidewall thermal insulation, and we compared this with the same 10-stage structure but without the sidewall thermal insulation. And you can see there is a very large temperature energy efficiency drop. It drops from the 400% to below 300%. That's why the sidewall insulation is super critical for the design of this multi-stage structure. Here, I would like to show a representative video of the starting up stage of this multi-stage device. And as you can see here, immediately after the experiment starts, the first stage here is activated, and there are droplets of water keep flowing out. And then the rest of stages are gradually activated, and you can see the continuous liquid flow. Basically, they are in order, and they are doing this. And for the remaining stage, the last several stages, it takes a relatively long time to see the liquid flow out, because it needs some time for the water inside each stage to accumulate for a while to overcome the capillary pressure generated at this outlet. And that's why we see it will take about more than 1 hour to get all the stages be activated and be seeing the water flowing out. This is longer than the time consumed for reach the thermostatic state. So we can see after this about one half an hour, all the stages are activated and keep produce water from this device. Then we compared the performance, especially the energy efficiency and the production rate of our prototype with existing passive small scale device. As you can see, although there are several very recently there are several approaches to reuse the vaporization enthalpy and break this 100% efficiency limit, but they demonstrate about 200% total energy efficiency using the electrical heating. However, with advanced understanding on the overall heating and mass transport, we almost doubled their performance in our design, and we can use the direct natural sunlight instead. And for the rest of studies, just using evaporation on the single stage, they are fundamentally limited by this 100% efficiency, since they cannot reuse the vaporization enthalpy. And another very important thing we are also interested in is the desalination performance and salt rejection performance. So for this reason, we performed the desalinity and the salt rejection test in our study. So we show we compared the salinity before and after the desalination, and we show it decreased more than 4 orders of magnitude after the desalination process. This is also like more than 2 orders of magnitude lower than the drinking water standard proposed by the WHO. And the water salt rejection, salt accumulation is also a severe problem for the typical evaporator, since during the evaporation, the salt will live on the surface and it will crystallize and accumulate on this evaporator and further degrades the evaporation performance. So we want to study like if our device has a sufficient capability of salt rejecting. So that's why we do this daytime and nighttime simulated cycling. So we place our device like under the 1.5 sun illumination. This is a very extreme situation that for the continuously running it for 3.5 hours. So the total solar radius is about 5.25 kilowatt hour. So this is larger than the average daily solar radius of US, which is 4.5 kilowatt hour. So we would just want to simulate an extreme situation. And as you can see that after 2 hours of operation, the salt becomes crystallized and it evolves along the surface. And for the visual guide, we use the black dash line to show the evolution of the salt accumulation. And after the 3.5 hours running, like we turned off the solar simulator and simulate the nighttime condition, that is no solar flux. And the salt is able to diffuse back to the bulk liquid, which is driven by the concentration gradient, because here the salt has very high concentration, but for the bulk liquid, it has relatively low salt concentration. Due to this gradient, the salt can diffuse back to the bulk liquid. As you can see, I use the white dash line as a visual guide to show the evolution of the salt. And after 50 hours, so all the salt accumulated on the evaporator diffused back. So this means like the device we developed has a reasonably good like salt rejection capability, and it can be continuously run during the daytime and nighttime cycle. So all the previously tested and experiments we are performed in the laboratory conditions. So this is a very ideal and very well-controlled environment. So all the performance data we got is desired data. But we are also want to know the realistic performance by putting the device in a more like real conditions. So that's why we put why we perform the water production test on the rooftop of MIT. And we choose a partly sunny day because we want to get the average weather condition. It's not a perfect weather condition. And as you can see here, you can see the cloud on the sky, which decrease the solar flux. And we mounted our stage on this aluminum frame and tilted 30 degrees to face the sunlight. And we fix this position, it doesn't change during the entire test. And we also put a panometer with the same tilting angle of our device, and this can measuring the incident solar flux. And we use the same experimental configuration to measuring the temperature and mass simultaneously. Meanwhile, like we use a cylinder to collect the desalinated water as shown here, and we use a camera to monitor the increase of the water level during the collection process. And as you can see here, the temperature rise became very similar in the laboratory conditions, but it's very fluctuating due to the non-ideal weather conditions. And as you can see, this fluctuation is mainly arising from the fluctuation of the solar flux. It can be seen here. And this fluctuation of solar flux is arising from the moving of the clouds because it shadows the sunlight. And the average solar flux is also lower than the experimental condition. It's only like about 650 watts per meter squared, you can see here. And each spike you observe here, and you can see there is a temperature drop and the recovery cycle corresponding to the spike of the solar flux. And during a like 4.5 hours operation, like we collected 72 milliliter water in this cylinder. As you can see, like we use a tiny device and we can extract a glass of water on the rooftop. Although like the performance is non-ideal because corresponding average like productivity is only 2.6 liter per kilowatts per hour. So this is actually more than 40% degradation compared to the experimental condition. but this value is still higher than most of the state-of-the-art technology developed around the world. So here I would like to show a representative video about the outdoor test performed on the rooftop of the MIT. And you can see here we tilted our device and facing the sunlight. And you can see the clouds is moving reflected by this optical table, which generates fluctuation of the solar flux. And the first stage is activated immediately after the experimental start and the water flowing out. And the rest stages are activated gradually. And you can see the water level in this graduate cylinder is rising with time. And we perform this water collection to show the desalination capability. And during this like 4.5 hours operation, that we can collect a glass of water using this tiny device. All right, in conclusion, so in this study, we focused on the strategy for the small-scale passive solar-driven desalination system, and then we proposed the concept of thermally-localized multistage solar scale, which take advantage of both the interfacial solar-driven evaporation and the multistage structure to recycle the vaporization enthalpy. So we developed a heat and mass transport coupled model to have a better fundamental understanding on the performance limit. And based on this, we proposed the specific design deadline and optimization principle for our system. Especially, we optimized the number of stages we are required and the optimal like air gap thickness and the required thermal sidewall thermal insulation to maintain the performance. And in the laboratory test, we demonstrated the record high energy efficiency of over 385%, which corresponding to the water production rate at 5.78 liters per meter square per hour. And the total material cost is very low because the single unit price of our material cost of our setup is about $1.5. And we also demonstrate good desalination performance and reasonably good free of salt accumulation capability of this setup. And more importantly, like through this work, we would like to emphasize like in addition to the material level innovation, that we believe an in-depth understanding of the fundamental heat and mass transport and their device level optimization is also very critical to further improve the water production rate using a very low cost and more scalable architecture. But we believe that this kind of thermal perspective and the thermal breakthrough can further gap the bridge between the laboratory prototype and the market product. So we hope that our efforts will provide a reliable solution for the future clean water production. So I would like to thank Professor Evelyn Wang, my advisor, for her great support and guidance into this project. And I would like to acknowledge my key contributors about this project, Zhenyuan Xu and Lenan Zhang, who co-led this project with me. And I would like to thank collaborators from Professor Ruzhu Wang's group at Shanghai Jiaotong University in China and Professor John Linhart's group at MIT. And I would like to thank all my lab mates in the device research lab. Thank you for your attention today and thanks so much for your time. Do you have any questions?
Lenan, thank you very much for the wonderful talk and wonderful work. And I send my virtual clap here in video.
Thank you so much.
So attendees, if you can please use the question and answer functionality to ask your questions. I think that's probably the most streamlined way to do it. But as to just kick it off, I do, in this interesting time, I'm very tempted to ask for a prototype and to go do my social isolation on a salty beach someplace and to generate some fresh water all by myself. But the question that I had is you had shown some optimization across the several parameters of stages and the air gap and the thermal insulation, individual parameter at a time. Is that how you did it, or do you actually do a multi-parametric optimization? And is the problem a convex problem? So that's
it's basically a multi parametric optimization. because like for each fixed configuration, for each like fixed height and air gap thickness, there is a peak efficient, that's a saturation point. And then we optimize the saturation like a point by varying with a geometric configuration. So this is basically what we found is a global optimization, and each parameter reaches optimal value.
Very good, thank you. Okay, so we have some questions coming in. First question I'll take is from Philip. He said, the first part is, I don't understand the efficiency being greater than 100%. The enthalpy rate of vaporization cannot exceed the solar heat input.
Yeah, this is true for a single stage, because like if you don't convert the vapor, condense the vapor into the liquid, the enthalpy will from the thermal energy will also always continue in the vapor phase. However, like for the water desalination, you always need to convert the vapor into the liquid state. And during this process, it releases energy to the environment again. And this energy like can be reused to drive more evaporation. So this is typically used by the community as energy efficiency. However, this is very similar to the if we learn the thermodynamics, it's similar to the COP of the air conditioning. So it can beyond 1. Like for the air conditioner, like it can be higher than 1, it can be even 4 or 5, because like the heat carried by the air conditioner can be more than the total electricity input. But similarly, like the water production by the system can be more than by the solar energy input. So this is like my answer. I'm not sure if you have a clear understanding to this. Yeah. It's a little bit confusing just because the definition of the energy efficiency, but community typically uses like water production times the latent heat over the solar input. But this is very tricky, like we can reuse the energy during each time the condensation and drive more evaporation. That's why we use the multistage.
Very good, thank you. Philip had a follow-up question. What is C optimal? Are you mixing the coefficient of performance with thermal efficiency?
Because like most previously, like to drive this sufficiently high solar evaporation process, they need to concentrate the solar flux. So the Q prime represents the natural solar flux, for example, 100 watt per meter square, and the COPT represents the optical concentration factor. So if you concentrate it twice, so you get higher intensity and you get higher flux, and in theory you can have better performance. For example, like this material based on the plasmonic solar absorbing, and they use like highly concentrated solar as an incident flux, like the COPT equal to 40. So this just representing the strength of solar concentration.
Very good, thank you. There's another question from Finley. Is there more information available on your simulations? Either, I guess, in publications or as additional material that you can share.
We have 2 papers about this work. The first paper is about the modeling. Since it's modeling, although I briefly go through it, it's quite complex. So we applied a paper this year. We published a paper this year on the Journal Applied Energy. And if you are interested, you can log in our group website, the drl.mit.edu, and you can find this paper. It's a modeling and performance analysis about multi-stage thermally-localized desalination technique. And the second paper about this is experimental demonstration, which is the main body I showed today. And we also published a paper on the Journal of Energy and Environmental Science this year, and you can also find this paper. And the title is the same as the title I present today, the ultra-high efficiency desalination via thermally-localized multi-stage solid steel. Yeah.
Thank you. And what we will do is when we send out the link after this talk with the video link, we will also send links to those papers or to the webpage, so it'll be easy for the participants, the live ones now or in the future, can see it. So that'd be a great follow-up. So we'll take one more question here, just in the interest of. I think Mohammed had the next one. The usage of silica aerogel could hinder the scalability of your product. What other materials are you considering to scale up? And I'll continue this question just so you have it. Also, it seems after certain stages, the product efficiency is not impacted. Have you considered comparing increasing the surface area of exposure versus the number of stages?
Yeah, that's a very good question. Like silica aerogel is indeed a very unique material, but it's actually not so necessary in this, but it can always improve our performance. So basically we can use like a typical anti-reflection coated like glass as a cover to reduce the both convection and the conduction heat loss. But the performance will be a little bit worse than silica aerogel because aerogel has the superior spectral properties. And silica and our group are also working very hard to push the silica aerogel to commercialize. For example, like our group member Elise and Kyle White, they have a new startup. Like the aiming of this startup is just like increase the spendability, and by using the aerogel as a better thermal insulation material and some solar window for that. So I think there are definitely great opportunity for both finding the alternative material and both further extending the capability of the silica aerogel. And for the area, it's also a very, very good comments. Like it's a critical point. Like people like typically use like water production per area. So since we use multi-stage, so the water production rate per area is very high. But we don't need that much stage. First, for several reasons. Firstly, the material cost. The material cost is relatively high because we multiple the number of stages. And secondly, the benefit from the number of stages is not always so positive, especially the number of stages high. And thirdly, the thermal mass of the multi-stage system is quite large. As you can see, it takes about 1 hour to get like all the stages activated. So, so ideally, like we would like to put this device, single unit device, into an array. And for example, like 10 times 10 array, like by putting 100 unit devices to occupy 1 meter square area. And the total production of this array will be 10 liters to 20 liters, which can satisfy the demands of the maybe 2 adults per day. So this can satisfy the water consumption, drinking water consumption of the small family scale. And another question is like why this device is small? Because this is we use a passive capillarity to supply the liquid. So the material height, especially the height of the device, is limited by the capillary force or the capillary length. So typically the capillary length of the material is like 10 to maybe 50 centimeters. So this limited like the single device, the single unit size cannot be larger than this size. So that's why like we start from a very small prototype.
Very good. Thank you very much for taking all those questions, and again for the very wonderful talk. So again, my virtual claps.
Thank you.
So I want to ask Teresa if she can bring up our ending slides. As you know, we're having this weekly series to continue to engage with the community. Our model is to have 1 week a talk from a faculty member, and next week a talk from a graduate student or postdoc. And then in the third week, a talk from an outside partner. Mm-hmm. Next week, we will not be having a talk. We'll be having an internal event for our students, an MECI Alliance Seminar Series Alumni Panel. So it's an internal event. So next week, we will not be hosting a talk. But the following week, we will. So Teresa, if you can please go to the next. Professor Ellen Roche of Mechanical Engineering in the Wednesday, May 6th at the same lunch hour, will be presenting some of her work on novel manufacturing technologies and device translation, medical device translation. And then in the following week, we'll be hearing from an outside partner. So again, I thank you for your time and attendance, and please reach out to Lenan with your further questions, and we will be posting today's talk onto the MECI Alliance webpage along with links to the paper. And the last point, if we can just advance one more slide, is that we would like you to reach out to us. We want, whether you're a student or MIT faculty member or an industry partner, we would love to have you at the lunch hour present. Share your ideas, your research, the things that you're interested in looking out for connections with the community. And it's a great way to stay intellectually stimulated in a rather relaxing way. And if you have recommendations for how we can improve this event and reaching out to you and to others, please let us know. And I thank you for your time. Lenan, thank you again for the great talk. And
thank
everybody
you so
else.
much for coordination.
Our pleasure. Thank you.
Okay.
And see everybody again in 2 weeks for Professor Roche's talk. And have a good day. Thank you.
Thank you,
Okay.
everyone.